As you might know, most colored images that you have on your computer consist of pixels where red, blue, and green components have 256 possible brightness values. Now suppose you had an image like this and you wanted to display it on a monitor with pixels that weren't capable of the 256 different brightness values. As an extreme, suppose you could either have full intensity of that pixel value or complete darkness. There's no intermediate brightness values. The question is, what do you do for a pixel that has sort of a half intensity or brightness value? The most straightforward thing to do if you wanted to display an image on a monitor like that would be to look at each pixel individually and either round up to complete brightness or round down to complete darkness based on the original brightness value. There are issues with that, however. You tend to massively increase the contrast of the image, making it look mostly unrecognizable. The main way to get around something like this is through very clever use of image dithering algorithms, which has to do with the diffusion of error in an image. And that's what we're going to focus on today. If you guys want to support the channel and learn how to code just like me, I highly recommend checking out my Udemy course, Python STEM Essentials. Coupon code in the description, you can get the course for $10 for the next 5 days. So the packages we'll be using today aren't too complicated. I have NumPy as usual. To load the images we'll be using today, I'll use the PIL, the pillow library. I also have matplotlib, so we can actually look at some of the images after we apply the dithering algorithms, and then Numba as well. And the reason we'll use Numba is because the algorithms used for dithering are inherently sequential. So that means that each operation in the algorithm depends on the previous operation. So it's very hard to parallelize this sort of algorithm and put it on a GPU like you've seen me do in my other tutorial series. Because it's sequential, it needs to be run one after the other, and that's difficult to optimize on a GPU. But that's what a CPU is really good for, because a CPU can apply operations very quickly. And so Numba will basically allow us, rather than using the slow sort of looping capabilities of Python, Numba will obviously takes Python code, and if you use the just-in-time or JIT compiler, you can write Python code, it converts it into a pre-compiled format, and every time you run the function, it actually runs very quickly because it converts it to sort of a C equivalent type of code. So we'll import the packages. So to motivate something like image dithering, it helps to look at sort of basic examples. And so what I'll do is I'll start by loading just a simple black and white image where the intensity or the magnitude of each pixel value corresponds to the sort of intensity or brightness of that pixel. So I have this image that I'm going to load here using the image library. I just give it the file path. The data, well, this image, if I just look at this, if I just open this image, it's not actually in an array format yet. It's actually the image itself, and you probably recognize this person here. I need to actually convert it to a NumPy array so that I can apply the algorithms to it. So for that, I just call mp.array on the image. I convert it to a 32-byte float, and then I divide by 255 because the range of values, you know this with images with color, they go from 0 to 255. The same thing with black or white. And so by normalizing by 255, it makes sure that everything is between 0 and 1. So I convert this image to data, and so that just gives me basically a NumPy array like this, a 2D sort of image. And then because the shape of the data, if I look at the shape, that gives me sort of the dimensions of the image. It's 280 by 300. When you have a colored image, you also have 3 channels on the end for the red, blue, and green intensities. Because I'm going to write the algorithms to loop over the color channel as well, I'm just going to give it another axis. So in this case, the length of this particular, or the shape of this data is 2-dimensional. So I'm going to add an additional axis here. So if I run this and I look at the shape of data at the end, you can see that it's actually added this 1 dimension at the end. And of course, if it's a colored image, there'd be 3 dimensions at the end. And that just makes sure that whether we're in black or white or colored images, our algorithms can be written the same way. And we can loop over the color channels, whether there's just 1 for black or white or 3 for red, green, blue. And of course, if I look at my data is basically just an array of numbers here, where each number, the higher the number is, the closer it is to white or a bright pixel value. And the lower it is, the darker it is, or the less sort of shine there is. And so if I were to display this image on a monitor, some sort of display device, I would need control of the pixel intensity in every one of the pixels. So most monitors these days, they can give varying levels of brightness in a monitor, but some older sort of monitors, especially old display sort of things you would see at sports stadiums, they're not capable of adjusting the brightness of each pixel, and even some older computer monitors are like that as well. And so they can only be on or off. You can't actually have a half brightness to them. And so these pixel values that you see here do correspond to sort of a half brightness. They're not fully on or fully off. They're sort of somewhere in the middle. And so the question is, how would you best display an image like this with these values that are sort of gray, not totally black or white, on a monitor that can only display black or white only images? And yeah, here's the image itself. So you can see that a lot of these pixel values, of course, are gray. Some are black, some are white. And I'm saying, suppose you want to display this on a monitor that's only capable of black and white pixels. What's the best option there? So obviously the most naive way of going about this is just to round the values. So for example, if I look at my data array like this, and I see all these values, I could take anything that's less than 0.5 and round it down to 0. And I could take anything that's greater than 0.5 or greater than half brightness and round it up to full brightness. And so that's what this np.round function does. I'm just rounding all the numbers to their nearest, either 0 or 1. But of course, if I plot this, I get something that looks sort of terrifying here. You can see that anything that's sort of the darker grays goes to black, and anything that's slightly white goes to white. And I get this, I don't quite know what this is here. But it's certainly not what you would want to display on a monitor. And there are algorithms that can get you to display this image and actually make it look pretty good, even if you're only using black or white pixels. Basically what's happening here is this: if I were to adjust the contrast of this image in some sort of photo editing software, what's happening is I'm dragging the contrast up to the extreme. So the contrast is the sort of contrast between bright and dark pixels in the image. So in the case of the normal data that we loaded, sort of these values are closer together, and et cetera, et cetera. And by increasing the contrast, I'm making the lower ones really dark and the brighter ones really bright. And so I get this extended sort of contrast looking image here. Now the question is, how can I only use black and white pixels but maintain, at least perceptively, a contrast that isn't so extreme like you see in this image here? So that's where dithering algorithms come into play. And these sort of algorithms have been used in older computer monitors. I think the older Macintosh monitor actually used these algorithms to display. And the way to sort of motivate and establish the paradigm of these algorithms is you have to consider the error that's induced in each pixel when you round it. So for example, if a pixel value is supposed to be 0.7 and I round it up to 1, then that's an error of 0.3. So we have to start quantifying how these errors are defined. So if I consider a pixel ij, it's a sort of 2D coordinates, and the image I call I accepted, I guess is what this stands for. This is just notation in a paper I found. Every time that it's rounded, it accumulates an error e, right? If I'm rounding to 0 or 1, I'm going to get an error as I make it either brighter or darker. And so the error is just defined as the original image here. So maybe it's 0.7 at this particular voxel. It's some sort of gray, a sort of lighter gray color, and then I round it up to white. And so this is really bright. So I have maybe 0.7 minus 1. I get an error of negative 0.3. And I out is going to be the rounded image. So this is just either ones or zeros in this case. And so the error, I can interpret the error either being positive or negative. Well, if the new pixel, if I round it and it gets brighter, so I out goes to 1, then the error is going to be less than 0. And if the pixel is too dark, if E is greater than 0, well, then this is going to round down to 0. So it'll be like 0.2 minus 0, for example. And I would get E that is positive. So you imagine that every pixel I round in this image here has an associated error with it compared to the original image. The idea behind the whole dithering algorithm is to try to diffuse this error across neighboring pixels. So what exactly does that mean? It means that if I were to take one pixel that's at 0.7 and I round it up to 1 and I make that pixel brighter, it means that I need to make the other pixels surrounding that correspondingly darker. So if I make one pixel brighter, I move everything else around that image and make it a little bit darker. And that's sort of vague how I'm describing it. It's very qualitative, but it's discussed pretty well in this document here. And this is a great example, actually, they have in the paper. So, and this is a great example they have of dithering in this paper. So you imagine that you have a gray image. So everything is 0.5. Everything is halfway between being dark or white. It's not full bright, it's not full dark. It's just a gray image. And I want to know how I'm going to apply the dithering algorithm to make this new output image. Remember, things can either be bright or dark. And in this case, I think they round down with 0.5. So anything 0.5 or lower is going to be a dark pixel, and anything that's 0.5 or greater than 0.5 is white. So if I just took this image, which is gray, and I rounded every one of these pixels, I would be rounding all of them down to black. So I take a gray image and convert it to a black image. And so that would be totally changing the nature of the image in that case. And so the way that dithering sort of works is like this. So you imagine that, and I'll go over the equations in a sec. This is sort of qualitative for now. You imagine that I take this pixel here, and this is going to be the output image. We don't know what it looks like yet. You have to go through the algorithm. I take this 0.5 and I round it down to 0 here. So you can see that in this first iteration, I make this pixel black. So I've rounded it down to 0. So when I round it down to 0, that pixel is going to be a little bit darker than it otherwise would have been. It's supposed to be gray, but we've made it black. And so the way to adjust for that is you adjust these values in the original image so that they become a little bit brighter, because we've lost brightness in this pixel. So we're going to increase the brightness of the surrounding pixels. And so this has sort of been done. This has been set to black. And now I need to sort of go to the next iteration. So then in my next iteration, I look at this pixel, which has been now changed from 0.5 to 0.719 to adjust for the fact that the pixel beside it has gotten a little bit darker. And so in this case, 0.719 rounds up to 1. And you can see that, of course, the corresponding pixel here is now white. And so I've made this brighter than it should be. And I've made it about 0.3 brighter than it should be. So the error associated with that is of magnitude about 0.3. So what I need to do is, because I made this pixel brighter than it should be, I then need to adjust all the pixels surrounding it, here, 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 and here, to be a little bit darker. So in this case, this 0.5 gets tuned down because the pixel's been made brighter than it should have been. And this one as well, and then the one below it. Well, this was originally adjusted higher because this one was dark. Now, because this one is extra bright, it's been adjusted lower again. And you can see that it's actually lower than it started off. It started at 0.5, then it got a little bit brighter because, of course, this guy right here. And then finally it got a little bit darker, and that's because this white pixel is actually closer to here than the black pixel is. So, of course, it should be a little bit darker. And anyways, you continue in this sort of format on and on and on, and eventually, in the end, you get this sort of checkered-looking image. And of course, this is one sort of portion of the entire image. If this were a large image and you were to zoom out, and there were hundreds of pixels in each dimension, this would be perceived to the human eye as being gray, as opposed to if I just rounded down every pixel. So the main question you're probably asking now is, what are the mathematics involved in adjusting these neighboring pixels here every time I iterate through a given pixel in the output image? That's basically these equations here. So imagine that I'm at the pixel ij here, and then I round it to get the output pixel. Then I define the error, as I did, of course, in the code that I have here. This is the error. And then I adjust all the neighboring pixels of my original image based on that error. So the error, of course, if I round from 0.7 up to 1, the error is going to be negative in that case. And then what I do is if I'm at point ij, I then change all the values of the neighboring pixels of the original image based on that error. So this pixel, which is originally 0.5, it goes to 0.5 plus 7/16 of the corresponding error. So if the error is negative, it's going to be a little bit darker. So it's going to move down a little bit. So then what we need to do is we need to implement these equations in Python. And of course, if you go through this procedure, it's like running over a for loop. And in Python, as you know, for loops are extremely slow because it compiles line by line. Of course, there are packages out there to get around that, and we're using one of them. We're using Numba. So the advantage of Numba and the just-in-time compiler is that it converts the code that you write into C code or something like that so that it runs extremely fast every time you call the function. So it actually makes it so that looping in Python is extremely efficient. And we can remove the Numba sort of header here, and you can see how much slower it runs if we don't use this optimized code here. And so I use the Numba just-in-time compiler. I have to specify my input and output argument. Both are 32-bit float arrays. Remember, they're just individual numbers where the intensity is how bright something is. And of course, there's length, width, and color channel. So that's why I added this extra dimension here, because whether I was using black or white or color, I would have had to change the input arguments to this function, which is sort of annoying. So I just black and white, I make it so that there's this additional color channel dimension. So it loads in the image, which of course is a 3-dimensional array where the last dimension is color channel. It gets the dimensions here, and then it basically loops through the rows, columns, and color channels. I start by rounding the pixel value here. So I get, if it's of course greater than 0.5, it rounds up to 1. I define the error as I did in the equation above, and I set the value of the image equal to its rounded value. So that's the first part of the algorithm. And now I need to adjust the neighbors according to these equations here. So the only complicated thing about that, of course, is I'm indexing I plus 1. So if I'm at the right-hand side of the image and I want to adjust the neighbor to the right of that, well, of course, it doesn't exist. It ends abruptly. So I don't do this if I'm at sort of the right-hand side of the image. The same thing if I'm at the bottom of the image, I can't index j plus 1. So I put these little Boolean checks in the code. So if I is less than lx plus 1, if I'm not at the right side of the image, then the image gets adjusted as follows here with the corresponding fraction and the error. And then if j is less than ly minus 1, well, then I adjust these 3 neighbors below it as well. The first thing is that the neighbor directly below it gets modified using 5/16 of the error. And then if I is greater than 0, well, if I equals 0, if I'm at the left-hand side of the image, I can't adjust the neighbor to the left of it. And of course, the same check occurs here. So it's basically just a very simple loop over the image. And if I run this code on the data that I have and I show the image, you could see that, well, it's not perfect. It certainly looks a lot more like the original image than this image that was just occurred through rounding. So this image is only made up of white and black pixels. I think matplotlib, maybe the resolution that it's showing here, it actually kind of shows up as gray. The important thing about this is if I look at this image, because it's shifting the error in such a way, it preserves the general intensity locally of the image. So for example, if I take a little box here of all these pixels and I sort of average it, it's going to look like the average of these pixels here because the error is being diffused. Whereas here, everything is being scaled either up or down. So of course, if I take a box here and it's totally black, then it's very different than the original image. So it sort of preserves this averaging over local regions by diffusing the error throughout the algorithm. So Floyd-Steinberg was one of the earlier dithering algorithms. Later on, there was Atkinson dithering, and this was the one that was actually used on the original Macintosh monitors. And so there's a summary of the dithering here. And so you can see that this is sort of a diagram of the Floyd-Steinberg error, that you adjust the one to the right by 7/16, bottom right by 1/16, 5/16, 3/16. And it works pretty well, and you get sort of these images that look like that, as you saw in the video. The Atkinson is a little bit different, and there's a sort of a special feature to this one as well. You can see that I'm actually adjusting neighbors 2 spots away from it. And unlike the Floyd-Steinberg, where if you add up all these errors, they add up to 1, the Atkinson algorithm, all these values actually add up to a value less than 1. So you have to think what exactly that means. I'm not distributing the full error to all the neighboring pixels around it. And you could think of the original just simple rounding algorithm. You're putting no error in the neighboring pixels, and you massively increase the contrast. What happens is if you don't distribute the full amount of error to the neighboring pixels, you're actually going to increase the contrast of the image slightly, because it means that all these pixels aren't being scaled enough based on the amount of rounding that occurred here. So it's basically the same to implement as the Floyd-Steinberg algorithm, only of course there's a little bit more checking that needs to occur for, pixels that are 2 away from the image that you're at. So it's basically the same code here, of course, implemented in Numba. And I can run this code and I can get the Atkinson version of the dithering. And so I can look at both images, and you can see that they sort of show up a little bit differently. And if you just sort of subjectively rate the image quality, although this one preserves that averaging property, if I take little regions here, this one tends to look better to the human eye. It seems like there's a feature that when you sort of digitize things like this, by increasing the contrast, it helps preserve the subjective quality that we give to an image like this. But what's happened, of course, if I take a box here and I take a box here in the original image and I look at the average sort of value and compare the error, this one is going to have a bias to it because there's contrast that occurs. You're increasing the contrast here. And sure enough, if I sort of decrease this fraction to 1/6, then I'm preserving the error and I can look at the two images. Well, then they start to look more similar. In contrast, if I sort of make the fraction 1/10 as opposed to 1/8 here, I'm going to be sort of diffusing even less error to the neighboring pixels. And if I look at this image, of course, you get even more contrast, but it doesn't look quite as good. And so I guess they found that an optimal value is about 1/8. You're not distributing all the error to the neighboring pixels, but it looks pretty good. And so the original monitors for the Mac OS, when they displayed an image, they would use an algorithm that sort of looked like this. So what I have here is a full large color image. It's a picture of a boat or something that I've saved here, and I'm going to open it. I'm going to apply both the Floyd-Steinberg and the Atkinson algorithm to it. And we can look at all three images here. And you can see that this is a fairly large image. This is about 2600 by 3600 image. It's very large. And what happens is if I apply the Floyd-Steinberg, because the resolution is so fine in this image, you almost don't notice anything. Now, this isn't true for the Atkinson, which increases the contrast. You could tell that this image here certainly has a higher contrast than these two images. So by using the Atkinson algorithm, it's almost a method to increase the contrast of an image. You can't see the differences unless you really zoom in. So if I sort of zoom in to one little region here, you can see where this sort of Floyd-Steinberg and Atkinson and the original start to differ. You can see that here, of course, this is all black, and here you can see some red and green and blue pixel values. When you zoom out far enough, the human eye, which acts as a low-pass filter to some extent, will just sort of average over these red and green areas so that if you look at the image like this, it essentially just looks black. Now what I'm going to do just to end this video is I'm going to show how slow this runs without Numba. If I remove this header here, I redefine this function and I try to run this on this fairly large image. Rather than running almost instantaneously in 0.6 seconds, I assume it's going to take about 30 seconds. Okay, so it's been about a minute. It's still running. I don't really care how long this takes because you just shouldn't implement this algorithm this way. You should always use the Numba header. Whenever you're doing something that's easy to define sequentially in Python, I would recommend using this header here. Anyways, that ends the first video in the image processing series. Of course, we'll be doing more stuff in the future as well. If you enjoy the series, please be sure to like and subscribe. Join the Discord server as well, and I'll see you next time.